Good afternoon, everyone participating today. My name is Ann-Sofi. I work at SAS as a project leader. And SAS, Swedish Institute for Standards, for those of you who might not know, we are an organization that is appointed by the Swedish government to coordinate Swedish interest in international standardization in all areas except electrotechnical and telecommunication, but all other areas. And we are, as you can see here, we are a member of the European Standardization Organization, CEN, and also the Global Standardization Organization, ISO. And the standards that we're talking about here today are for industrial digitalization. And as you can see in this picture, you can see the relations between Sweden, Europe, and also the global organizations. And the standards within this area are being developed globally. And a lot of them are being developed within the Technical Committee 184. It's called Automation Systems and Integration. Yes, good that you're pointing there. And this technical committee is very big and consists of 3 different subcommittees with a number of working groups in each subcommittee. And as you also can see, we have IEC, which is electrotechnical standardization, and ISO and IEC are working together in many areas, but one is to look into smart manufacturing reference models in a joint working group. And on the national level, then we have a committee called 280. It's called Information and Automation in Product Life Cycle. And that is the SIS committee. And as a member in this committee, you can have knowledge about and also influence the global work that is being conducted in TC 184. And the membership in this committee is open to all interested Swedish stakeholders. And a number of those participating here today are engaged and being members of this committee. And today then, we are very happy to welcome one of the global leaders within TC 184 SC4, as you can see in the bottom. It's called Industrial Data. And he's a leader of a working group within this subcommittee that is called Digital Manufacturing. And in October this year, so very recently, the working group finished a standard in 4 parts. It's called ISO 23247, Digital Twin Framework for Manufacturing. And his name is Dr. Martin Hardwick. And
okay, thank you very much for that introduction. I would like to talk to digital twin manufacturing using the new standard that was just mentioned, ISO 23247. This is a framework standard that describes how to fit other standards together in order to make digital twins during manufacturing. The benefit of so doing is that we have these real-time models of the manufacturing, and those real-time models allow the development of applications which reduce costs, produce more accurate results, and produce them faster. The ISO 23247 standard is a framework. It can be used with many other data standards, but in what we'll be talking about today, we'll be using it with STEP NC, which is ISO 10303-238, or more concisely known as Application Protocol 238. And the thing about 238 or STEP NC is it takes the CAD models and associates machining solutions with them so that you can measure how well you're doing based upon the tolerances on those models. So it's all quite exciting stuff, because we have a framework, we have solutions, and we have the ability to measure on the shop floor using those models. So a little bit of background. I don't know how familiar people are with STEP. I imagine most people have got some familiarity with STEP. Also probably familiar with the idea that it's been around for quite a long time now. Started around about 1995 with the enabling of the exchange of solid models. Moved on in about 2003 to also reliably exchange assemblies of those solid models. Then with the first edition of AP242 in 2015, we were able to exchange annotations on those models so that you could visually verify what was happening. And now most recently, in 2020, we released edition 2 of AP242. ISO released it. And that enables the exchange of tolerances. And that's all work that took place in SC4, independently of my particular group. But the key takeaway is that STEP keeps expanding. Also, when we do these expansions, they tend to be of a pretty substantial nature. When we first in 1995 exchanged solid models, many people were willing to say that you could not do that using a neutral data standard, that you had to do a direct translator. And that's important to remember, because it did take 5 or 6 years for the exchange of solid models to become reliable. Now in 2020, we're exchanging semantic tolerances, and it's going to take 4 or 5 years for all the capabilities of that to work their way through the system. But it has started. We do see translators from CATIA and Autodesk and NX and many other systems that are exchanging AP242 with the semantic tolerances in them. So that data is becoming available to everybody, and the consequences for the manufacturing industry, I think, are going to be quite profound, because now we can reason about results and progress and make optimizations based upon that tolerance information. So that's what we're trying to do with STEP NC, is we think it's more efficient to put the manufacturing process into the same STEP file as the manufacturing workpiece, so that the results of each working step can be compared to the requirements for that stage of the manufacturing. So we have had 2 editions of 238. The first edition was enabling precision machining, and there are now large numbers of shims being produced using AP238 for commercial airplanes. We predict that version 2 of 238, which was released about this time last year, is going to become very important for the precision assembly of aircraft components. The way it's being done, largely speaking, is by combining your step file that comes out of your CAD system with an app.cl file that comes out of the CAM system that then can go into a digital twin application that the intelligent CNC can process and send back results using QIF, MT-Connect, and other standards. And I'll talk a little bit more about this in a moment. So what we've done most recently then is release the 23/24/7 digital twin framework for manufacturing. So that what we're looking to do is have lots of devices on the manufacturing shop floor, physical things, but also virtual things such as processes that are to be executed. There will be data collection going on with those processes, as well as dynamic control. Using these digital twins, which are the digitized version of the physical or virtual things on the floor, to then enable a range of new applications like real-time control, offline analytics, health checks, predictive maintenance, and so forth, with the new benefits of in-loop planning and validation, better production scheduling, enhanced understanding, dynamic risk management, and so on. So within this framework, we see STEP and STEP-NC being used to model these digital twins. And we see MT-Connect and QIF being used to send information from the shop floor equipment to those digital twins so that they can be updated in real time. So the key thing about the framework is it is, of course, all about making twins. It is only a framework, although I'm very much committed to using STEP and STEP-NC with the framework. Other standards could also be used. But it is, however, focused on manufacturing, with the communication protocols having been developed to be suitable for the shop floor, the manufacturing shop floor. Here's a more detailed version of the architecture. It is layered on the IoT architecture, which is 30141. There are these various functional elements which are suggested for helping the implementation. The digital twin entity, as I said before, is going to be a data model, a product and process model of what's going on the shop floor. Then we have the collection and control entities, which will be collecting that MT-Connect, QIF, or other kinds of data, which will be emitted from the observable manufacturing elements as they execute. So we observe at the lowest level, we collect at the next level, we model at the third level, and then we learn and act on those models at the fourth level. And this, as I said, is the ISO 23247 standard, and it was just published this month. So you can go to the ISO website today and purchase the standard. And we are now in the process of creating promotion materials to help people further understand how to use the standard and why they want to use that standard. So in order to be able to use this kind of framework, we have to be able to make digital twins. So one of the first things we need to do is develop a new pipeline that instead of making G code for machines, makes STEP-NC for machines. And that's been our focus for the last year or so, is creating the software systems to make this possible. As you know, in the existing process, the CAD operator will make a model. That model will be sent to a CAM operator as an IGES file, or it could be a step file, or it could be some other kind of file. But today's CAM systems are largely set up in the expectation it'll be a collection of surfaces in an IGES file that can then, the CAM operator can then create algorithms that will do the machining of those surfaces from whatever the stock happens to be. Once the algorithm exists as a process, it then gets posted using to G code, and that's actually quite a sophisticated / convoluted process, because every machine tool is different in many small ways. It then goes to the CNC, and now you essentially have a CNC operator who has to do the final stages of the debugging of that machining, and that is actually both tedious and stressful. There are good tools now like Vericut for making sure at the CAM level the process is good, and also the G code is good, but still things can happen on the CNC which were not quite predicted. So you do need an operator to watch that closely. Also, the operator with his ears is listening for efficiency and listening for potential problems like tool breakage. So it's an important part of the process. The to-be process for digital twinning is, first of all, we need to make it much quicker and easier. So we really can't have the CAM operator interpreting what needs to be made for the CAD operator anymore. If that has to continue, then digital twinning is going to be too difficult and too tedious. So we have to automate the generation of the manufacturing solutions from the step models with the tolerances. And we can do that today. Not for the most complex kinds of surfaces yet, but certainly for the kinds of features and processes that one defines for doing assembly sorts of operations. Then we need a CAD post to make a digital twin, but that can be quick and easy. In fact, the CAD guy mostly still makes a model, but it's the equivalent, we hope, not quite so easy, but the equivalent of publishing your document as PostScript or your PowerPoint as slides. We want it to be the CAD operator can publish the model as a process that can be automated, rather like additive manufacturing. A major selling point for additive manufacturing is that the manufacturing component, at least in principle, sometimes it's not so much in the practice, but in principle, it's a very easy thing to do. You push a button and out comes the instructions for a laser beam machine to essentially weld that part out of powder. We're now doing the same thing with Step NC, essentially push the button and that Step NC program gets created that can then go to a smart machine tool. And we think that machine tool of the future is going to be very analytics based, very intelligent, so that it becomes smart and easy to go ahead and do it, so that rather like in the good old days, you couldn't make your own slides, you had to send them to a specialist who would make the slides for you. Then the intelligence came along to make it possible to not use a specialist, we're getting to the levels now where you don't need a specialist anymore. You can just send the step NC file and have a smart control do everything for you. Again, it's not going to happen overnight. It's going to happen over the next 5 years, but it is going to happen at this point. And because it's going to happen, we're seeing the leading industry vendors, folks like Lockheed Martin and Boeing, and soon we believe Raytheon and other aircraft manufacturing, shipbuilding, advanced shipbuilding, are beginning to investigate what this new way of manufacturing looks like. So here is a test part that we've made. For historical reasons, it's made to look like an ashtray because automated manufacturing started at MIT back in the 1950s, and the first part they made using the APT programming system was this ashtray on the left here. Being of kind of historical minded folks, remembering the long history of everything, Lockheed Martin essentially is saying, okay, the new generation of automated manufacturing will do another ashtray to show that it's feasible. And that's what they've gone ahead and done, so that you can very quickly and easily make this ashtray with the minimal number of data entries, so that it should be reasonable for the CAD operator, the CAD guy who made the model, to quickly add in the basics necessary to also machine that model from some kind of stock. Again, not for the 5-axis advanced machining, at least not yet, but for basic machining of features for assembly operations. The parts will be very complex, but the features that will be machined will tend to be rectilinear in some space on those parts. Drilling holes, making pockets, cutting outlines, those kinds of things. So we have our enabling software that we're building for this. We're looking to minimize the time to make the digital twins. We're looking to maximize the opportunity for optimization and analytics. So we have the ability with the UI DLL to either make the 238 data. So we have the ability to make the data, and we're beginning on the ability to intelligently process that data, the beginning of what we might call twin analytics, where there's large databases of previous runs of similar operations on similar models, which are used to advise on the results, so that on the shop floor, it becomes quick and easy to do the machining, and quick and easy to get a reasonably efficient machining program. Okay, so with these capabilities, how are people going to take advantage of it? And that's something that we investigated heavily in the summer of 2020. We built some prototypes, some early prototypes that said, okay, if we have model-based machining available and the right kind of infrastructure, what can we do? And one thing the guys out of Boeing did was they need to have more flexible manufacturing. They have too often produced very large, very expensive machine tools, which will only work for one or limited configuration of airframe. More flexible machines are becoming available, The robots are an example of those flexible machines. They are not yet sufficiently strong to be drilling and filling holes, but machine tools that have the flexibility of robots and the strength of the machine tool for doing that kind of drilling and filling are going to be available very soon. So rather than have one machine, we'll have, say, 20, 30 robots on the shop floor. Those robots will most likely be on rails. And those robots are going to have multiple points of failure because different robots will be at different health checks, different availabilities. So the basic thing is that you need to be able to schedule and reschedule those robots dynamically without having to do your typical CAM process of making a single solution that requires everything to be set up exactly right. And then when it is everything is set up exactly right, you go ahead and execute it exactly as predicted in CAM. That is what still goes on today, and it means that the setup time for these processes is very long and expensive. You see these machines not doing very much for a long time until everything is ready for go, and then they do their thing quite quickly, and then they have to repeat with another long setup. Within the framework, with all the feedback, we showed that you could take a robot out the loop and quickly assign the work to another robot. You could change the configuration of the as-is wing so that some features were already on it. So you wouldn't have to do those, and that meant one robot had less work to do, so you could give some of its work to another robot. You could have a wing come into the cell which had been delayed for some reason. So if you had more time, you could get the robots to do more of the work and do some catch up. So you had some more flexibility in there. Because everything's model based, you have a model of the wing, you have a model of the process, you have a model of the robots, and therefore intelligent software on the shop floor can go figure out the best solution given that particular status. Another exciting application that we prototyped is based upon the notion of, although you'd love for manufacturing to be an exact science all the time, and it is, of course, it's not. When you are doing the composite layout of wings, for example, large dimensional objects with the variability of the whole layout process and the curation of the parts in the autoclaves, the actual skin that you get has different dimensions to the ideal that you designed. And this, of course, is where tolerances come in. As long as the actual skin is within tolerance, then everything is considered good. But in order for it to be within tolerance, you need to be quite generous in your tolerance limits. And as a consequence, you actually waste quite a lot of weight. And for advanced aircraft, the cost of that slight additional size is expensive. If we were able to measure every single hole and then do the stack up for every single component, do it dynamically, actually hundreds of pounds can be saved. And we know that's true because for the absolute most advanced aircraft like the F-35, they do take the time out to measure every single thing. But it's expensive, adds a lot to the cost of the aircraft. It's still too expensive for, say, Boeing to do it for their commercial aircraft. But with model-based manufacturing and models of everything and automated measurements, it's within reach that we can automatically compute the dimensions and therefore automatically select the best case fastener for each hole and thereby reduce the cost. The last use case is machining. This machining use case is based upon the idea of getting things done more quickly and making more economical use of all the available toolware. Again, when you have models of everything on the shop floor, you can also have models of how much material is being removed. And you know what kind of material is being done. You can therefore build your algorithms to know how much toolware is being applied at any particular point, and therefore make much better decisions about feed speed trade-offs versus available toolware trade-offs. You can't do this in advanced in the CAM system because you don't know what tool is going to be on the shop floor unless you're willing to start with a brand new tool every single time, which of course people do sometimes, but that is expensive again. Assuming that you're going to allow reuse of tools, second use of tools, then you need to plan it out correctly. If the tool is going to be more or less useless at the end of this particular job anyway, you may as well drive it as fast as possible to the end of its toolware. But there are other kinds of choices. You may want to do a swap in the middle and all kinds of things like that. But let me move on a little bit quicker. Just want to say that all these applications are becoming possible because of STEP NC, because of STEP and STEP NC having such a rich information model. It's that information that we're going to be using in the analytics on the shop floor. So encourage you to take a look at that information. You can buy the standard, but you can also, for example, go to our website and you can see the information and see how it's all related on that website. Returning to the 23/24/7 framework, again, it's designed to be flexible, but it's also designed to be used with what's practical on the shop floor today. So we have multiple networks, what's called the proximity network, going to the data collection entity, which could be a direct connection or some EtherCAT or OPC-UA, very good bus connection to the DCDE that does the data collection. The data collection can be efficiently done using something like MT-Connect, because you can process that as you are ready to process it, as you build your digital twin entities in your core. And then at the top level, the applications which are using this data, they can read and write models using the new network. So they could be using STEP, but they could also be using an administration shell. They're developing that administration shell pretty fast and furious at the moment. Or it could be some kind of open API. The point is that we have the framework available. It's a practical framework that can be deployed on the shop floor. It's also got the buffer between the observable manufacturing elements, which are making data at their rate, and the core digital twin entity, which is modeling data at its rate. Between the two, we have the DCDE, so that if the core entity can't quite keep up for a little while, it can move at its own pace. And then when it's ready, it will be updated and available for that information. So moving towards the conclusion here, we think that we're looking at the beginnings of a new state for manufacturing. It's been called Industry 4.0, of course, elsewhere, but we see that the realization of that state beginning to emerge. If you look at manufacturing today, there are still high-end applications where it makes the most sense for a CNC engineer to edit G-codes, to reduce cycle time, to get that extra feedback during the manufacturing from touch probes and so forth. That is, roughly speaking, the manufacturing equivalent of the assembly code programmer in software. And those people do exist still too as well, of course. To get the absolute fastest out of the operating system or a web browser, you have people go in there and reduce the cycles. It's expensive to do, but if it's going to impact large numbers of people or large numbers of parts, you go ahead and do it. But you've also got the second level. The level would be where what you want to do is so complex, it's really not practical to do it using G codes anymore. You've got very complex geometries to be machined. You need to have somebody who is an artist in some senses, creating a sophisticated CAM program that makes the best use of the available parts and has skilled design of processes and toolpaths. That is equivalent to, I think in the software world, to today's C++ programmers. They create many of these high-tech applications by making skilled use of CPU and memory, but they can't do that at the assembly code level because it's just too difficult. There's too many moving parts. They need powerful libraries that can be used to assemble the results. Just like the CAM operator, in order to be able to create a CAM solution for this complex part, needs to reuse libraries which are already in something like, say, MasterCAM. So that's been a very successful paradigm that has emerged in the last 20, 30 years, has become very much routine and is enabling the high-tech manufacturing of today with all the complex, smooth surfaces that we see, energy efficient, etc. But there's also frustration with this paradigm. Frustration because you do need that CAM operator and you do need his skill and expertise in order to be able to make effective use of that CAM system, because they're complicated beasts. Same thing has happened with C++ programming. That's great, but it's an expensive person taking a long time to create a solution. So in the software world, we now have even higher level languages like Python, like Visual Basic has been there for quite a long time, and to some extent C#, a new emphasis on ease of programming. So when you look at Python, it doesn't even bother with semicolons or any of that kind of stuff. It just says, if it's a new line, it's a new statement. It works most of the time, and it's meant to be used by people who've got to do a job quickly and efficiently, and probably maybe only once or twice. So there's no need for all that worry about user interface, etc., etc. We say that this is also now going to start to emerge for manufacturing. In order for manufacturing to become more efficient, we need to make it possible for a CAD operator to directly create a digital twin. And that is what we think is now becoming possible with the whole Step NC paradigm, and the combination of the quick ability to make the process, the reasonably quick ability to define, but you have to do it anyway, the ability to define the semantic tolerances, and the ability to combine those in an intelligent framework on the machine tool. It's all coming together to enable a new style of manufacturing where many people are able to quickly point at something, some feature, answer a couple of questions, and then get that feature drilled onto the assembly very quickly and easily. Not yet, not tomorrow, but in the next 5 years. So The only way to do this is to practice doing it, to eliminate all the unnecessary bottlenecks, to create the way that things should be done for your kind of industry, so that solutions do get generated quickly, so that analytics exists to make corrections on your kind of processes. So here my final thing is strongly asking people to think about getting started, to join Working Group 15 and participate in the development of these standards. We will be doing AP 238 edition 3. We'll start next year. It'll be the digital twin version of AP 238. We will be working on the second edition of ISO 23247. So there are useful ways of participating through SIS in Sweden. But there's also lots of high-tech manufacturing, of course, in Sweden. Saab, Volvo, Sandvik, your industries are very famous for quality. So I think you should be out there in order to stay ahead of the curve, identifying business benefits that can work with digital twin manufacturing. I described the 3 that we identified. And then looking at using models for that digital twin manufacturing, the twin models on the products going to be measured, the processes are going to be adjusted, and the hands-free automation that's going to result.
Charlotta Jonsson heter jag och jobbar vid Lunds universitet, och jag ska prata om det här projektet som vi kallar för 4S, eftersom namnet innehåller 4 stycken S. Strategies and Standards for Smart Swedish Industry. Och att arbeta med standardisering, ja, det är ju mycket viktigt för att svensk industri som helhet ska lyckas bli framgångsrik inom området för smart industri. Och det tror jag att alla vi som är här idag håller med om. Och vi vet ju också att det finns ett... Vad var det här? Det var något annat. Förlåt, det dök upp något på min skärm. Vi vet ju också att det finns ett nationellt intresse från till exempel Vinnova och från vår svenska regering att lyfta vikten av standardisering. Och vi vet att det är många svenska företag som jobbar med standardisering. Lärosäten likaså. Antingen genom att använda existerande utgivna standarder eller i vissa fall också att vara med och driva fram framkomsten av nya standarder. Men precis som vi vet det, så vet vi också att det kan vara mycket svårt att peka på och ge konkreta exempel på vilket värde det här faktiskt har. Såväl för enskilda företag som för...
Alltså jag tror det är viktigt att identifiera.
Hallå?
Nu är du mutad, Charlotta.
Unmute. Hör ni mig nu?
Bra.
Bra. Okej. Då ska jag säga så här. Samtidigt som vi vet att det finns det intresset, så vet vi också att det kan vara väldigt svårt ibland att peka på och ge konkreta exempel på vilket värde det här faktiskt har. Både för enskilda företag och för svensk industri som helhet. Och det här var något som vi tog med oss in i projektet 4S. Och när jag säger vi så menar jag mig själv, Lotta som jag sa heter, jobbar på reglerteknik på Lunds universitet med automation och industri 4. Jag är också ordförande i ISO TC 184 Subcommittee 5. Vi inkluderar också representanter från SIS och SEK, våra svenska standardiseringsorganisationer, och representanter från PIA och Produktion 2030, våra 2 svenska innovationsprogram, och representant från Blue Institute som är ett marknadsanalysföretag som vi har haft med i det här projektet. Vi satte upp 2 stycken mål. Det ena var att underlätta för svenska forskare och lärosäten och företag att aktivt kunna delta i arbetet med att ta fram nya internationella standarder inom det här området, smart industri. Och det andra målet är att klargöra standarders värdeskapande roll i industrihistorien och vad som händer nu när industrin digitaliseras, när vi går emot smart industri. Så de här 2 målen tänkte jag kortfattat säga någonting om. Och slutligen av presentationen säga lite mer om var, när och hur, så man kan få ytterligare information om det här arbetet. För vi hinner inte gå igenom alla resultat. Om vi tar gällande mål 1 här då, så vet vi att det finns inom flera av de industrinära forskningsprojekten som pågår i Sverige, så finns det många bra tankar och många fina resultat som relaterar till smart industri. Och de här tankarna och resultatet, ja, de kommer ju såklart till nytta hos både den akademiska och den industriella deltagande parten i de här projekten. Men vi vet också att flera av de här resultaten alldeles säkerligen skulle kunna lägga till grund och input som nya standardiseringsinitiativ. Och därigenom kommer ännu fler, både nationellt och internationellt, till nytta. Och här har vi inom 4S-projektet både identifierat ett gäng med sådana industrinära forskningsprojekt. Och sen har vi rustat dem både med kunskap inom standardisering och med lite finansiella muskler, så att de här personerna som deltar kan vara med och delta i standardiseringsarbete och föra ut de här svenska idéerna och resultaten. Och här ser ni lite exempel på sådana här industrinära forskningsprojekt som vi har identifierat, boostat med lite kunskap och lite pengar. Jag kan ta något exempel. På rad 2 här till exempel så har vi säkerhet för kollaborativa applikationer. Och det här är ett projekt som Chalmers har varit med i tillsammans med ett antal företag. Och vi har stöttat det här projektet så att personer kan delta både i det svenska och det internationella arbetet med att ta fram standarder för just kollaborativa robotikapplikationer. På rad 9 har vi in som handlar om digitala tvillingar också. Och här har vi ju fått en presentation av Gunilla Sivarts i det här forumet tidigare i höst. Vi har ett annat projekt, till exempel det är på rad 5, som handlar om development operations och som också som företaget Syntel bland annat är med i, och vi har också akademiska parter som är med här. Och här har ju pengar från 4S möjliggjort och underlättat för de här personerna att delta i arbetet med att ta fram en internationell referensmodell. Jag tror att vi har pratat om den någon gång här också om forumet, den här referensmodellen. Ett svenskt förslag har plockats fram och det har faktiskt fått väldigt mycket internationellt gehör. Så att det är väldigt viktigt att vi får ut våra svenska resultat. Och dels att vi använder det nationellt, men också att vi får ut det så att Sverige blir ett ledande land inom smart industri. Jag menar att vi boostar projekten och hjälper dem att ta ut, så har vi här på vänstersidan de industrinära forskningsprojekten. Och idén här är att ta resultat och idéer och föra in dem till de globala standardiseringsprojekten för diskussion där och kanske inkludering. En annan effekt är att man deltar här. Då lyssnar man också på andra globala förslag som kommer fram. Får den informationen med sig och tar tillbaka den kunskapen till de industrinära forskningsprojekten som pågår här i Sverige. Så den här snurran har vi försökt att boosta genom att ge lite pengar så att personer kan åka och delta på de här internationella mötena och sen föra tillbaka dem till de svenska industrinära forskningsprojekten. På så sätt så kommer de både akademi och industri till nytta. Så det var det ena målet där, att underlätta för fler svenska lärosäten och företag att aktivt delta i arbetet med framtagning av nya internationella standarder. Det andra målet som vi har jobbat mycket med handlar om att klargöra standarders värdeskapande roll i industrihistorien och vad som händer nu när industrin digitaliseras, när den blir digital. Ja. Här är vi just nu i projektet i slutskedet med att ta fram en skrift som på ett vänligt och intresseväckande sätt ska belysa det här, vilket värde det skapar. Den här skriften heter Teknik är silver, standard är guld. Och för att kortfattat säga lite vad man kan hitta i den här skriften så ska jag ha ner 4 punkter här till höger. Punkt 3 här är en presentation av de industrinära forskningsprojekten. Det var de jag hade på en lista här förut. De beskrivs kortfattat vad man har gjort i dem och hur man arbetar med standardisering. Vi har också punkt 1 och 2 här. Punkt 1 handlar ju om värdet av standardisering och standardiseringens utveckling genom tiderna. Så här tittar vi liksom bakåt och tittar på historien. Vilket värde har de haft? Vi tittar i punkt 2 på digitala förändringen som händer just nu. Och sen punkt 4 sist där så är det lite reflektion framåt om den fortsatta utvecklingen. Jag ska inte berätta allt som står i den här industrin, men jag kan belysa några aspekter i alla fall. Vad man kan hitta i industrin eller i broschyren. Den ska snart vara upptryckt och klar. Ja, men det händer ju supermycket i industrin just nu. Och den klassiska pyramiden här som vi ser på vänster sida med proprietär IT och industriell OT här. Den håller på att kompletteras med olika tekniker och aspekter som mer associeras till digitalisering. Det är det vi ser till höger. Exempel på det är ju IoT, Internet of Things, eller cloud-teknologin, eller 5G, wireless, eller avancerad dataanalys. Kan finnas mer här, 3D, simulering och så vidare. Värdet av den här sektorn som vi ser på höger sida, det vill säga den installerade teknikbasen, det har estimerats och den är ungefär 50 000 miljarder kronor. Det är det globala värdet på den här sektorn som vi kallar Intech. Så det är en stor sektor. Kommer tillbaka till det här senare. Ja, jag sa ju att det händer jättemycket. Den här bilden som är på vänster sida, den tror jag ni har sett väldigt ofta. Vi pratar om smart industri här i Sverige. I Tyskland pratar man om industri 4.0. Och det bygger ju på att det har skett 3 stycken kraftiga teknikskiften tidigare i historien. Och nu är vi inne på det 4:e teknikskiftet. Det vi ser på vänster sida här, då zoomar vi in på precis liksom övergångsfasen här från ett gammalt skifte till ett nytt skifte. Och det är precis i det här skiftet där som standardisering kanske är som allra mest viktigt. Om vi tar i förskiftet här, ja men där har vi haft mycket arbete som har gjorts av forskare, entreprenörer, i viss mån politiker för att etablera det nya som kommer. Och i efterskiftet här, ja då lämnar vi över till industrin för att ta hand om detta och leverera på detta. Tjäna pengar eller kommersialisera eller använda det på så bra sätt som möjligt. Men just precis i skiftet här så är det väldigt viktigt att många olika aktörer samarbetar. Staten, industrin, forskningen, innovationssystemet. Och det här är ju bland annat för att få standarder på plats så att de nya teknikerna som man arbetar fram här i skiftet innan, så att säga i S-kurvan innan här, att de kan börja samspela med varandra. Standardiseringen har ju också en avgörande roll för att befästa utvecklingen, inte bara under själva övergången och skiftet, utan också under lång tid framåt. Vi kan jämföra till exempel, det var någon som skrev i chatten förut om mobiltelefonin. Tänk om vi inte hade haft standarder där för att sätta 5G-tekniken, eller vi inte hade haft standarder för Bluetooth. Då hade det varit väldigt rörigt. Och det är precis sådana skiften som vi går igenom fast i industrin just nu. I rapporten så tittar vi också vidare på hur stor är den här branschen Intech. Som jag sa förut så världsmarknaden för Intech den har uppskattats till 405 miljarder US-dollar. Det uppskattas att det är en tillväxttakt på 6-7%. Tittar vi på vad det betyder för Sverige och hur det ser ut i Sverige så ser vi här till vänster att Sverige har en omsättning inom Intech på ungefär 105 miljarder kronor. Och tillväxttakten i Sverige har estimerats till ungefär 8%. Och här har vi har både våra IT- och automationsleverantörer med produkter av olika slag. Vi har OEM-leverantörer och systemleverantörer. Vi har maskiner till exempel som bostads med allt mer digitala inslag. Och vi har konsulter inom det här området. Tittar vi på Sveriges marknadsandel av den totala marknaden inom Intech så har den estimerats till 3%. Och det betyder att vi faktiskt, Sverige som nation, har en väldigt stor marknadsandel. En marknadsandel som kanske snarare ligger i paritet med vad länder som tunga industrinationer som Tyskland, Frankrike, Storbritannien har. Så Intech är ett väldigt stort och väldigt viktigt område för Sverige. Och då är det ju också väldigt viktigt att vi är med och tar fram de här nya standarderna. Att vi sätter riktlinjen för det nya som kommer. Och det här blir viktigt både för enskilda företag och för Sverige som nation. Allt det här, alla de här bilderna och mycket mer därtill finns i den här rapporten, skriften, som vi har valt att kalla Teknik är silver och standard är guld. Och här finns då mycket som beskriver just standardiseringens värdeskapande både historiskt, just nu och framgent. Det innehåller också en del spaningar framåt. Jag nämnde förut referensmodeller, vikten av industriell data, digitala tvillingar som Martin pratade om precis, interoperabilitet med mera. Och rapporten är tänkt att intressera personer som är intresserade av både huret och varför. Både hur vi gör teknikmässigt för att driva standardisering inom Intech-området, men även varför Intech och standardisering är viktigt. Bland annat de här ekonomiska aspekterna som jag tog fram här. Så för att sammanfatta så är det 2 mål som vi har jobbat med. Dels att underlätta för fler svenska lärosäten och företag att aktivt delta i det här arbetet med framtagning av nya internationella standarder inom området smart industri. Och dels att klargöra standardernas värdeskapande roll både bakåt, nu och framgent. Den här rapporten den kommer att vara klar och finnas i upptryckt format till nästa workshop som vi ska ha i det här forumet, inplanerat våren 2022. Så då kan ni få en tryckt kopia av detta. Den kommer väl vara kanske 50 sidor lång, något sånt. Och vår nästa workshop ska vi prata mer om alldeles strax i nästa punkt. Så med det vill jag bara tacka för mig och projektet Strategies and Standards for Smart Swedish Industry.